Hello there. Today we'll look at Sparse is enough in scaling transformers by researchers of the University of Warsaw, Google Research, and OpenAI. This paper on a high level proposes a set of building blocks to introduce sparsity into transformers, and this results in an architecture called the scaling transformer. In the second half of the paper, they then introduce additional features to the scaling transformer to make it into the Terraformer. Both the scaling transformer and the Terraformer, they're really fast at what they call unbatched decoding. Decoding is essentially inference in such a transformer model, and unbatched means that they can do this for a single sample. Of course, they're also faster in batched decoding, but I guess the effects are not as pronounced. And we're going to see why, because the sparsity really shines through if you have single examples and can only activate very small parts of the network at the same time. So the effect of all of this, at least for the scaling transformer, is right here. If you have a model with 800 million parameters, I guess today that'd be called a small model, the baseline transformer has a decoding time of about 0.16 seconds, whereas if you add all the tricks to the scaling transformer, you speed that up by a factor of about 2.6x. That's not that pronounced yet the effect really shines if you go to bigger models. So if you go to a 17 billion parameter models, the baseline transformer takes about 3.6 seconds on this particular hardware to decode. The scaling transformer with all the tricks activated takes about 0.18 seconds, giving a speed up of 20x. And so in different settings, on different configurations, these speed ups can in fact get even higher. I've seen up to like 37x or something like this, which is quite fast. And this all while the performance doesn't degrade. And that is surprising. So they say, surprisingly, the sparse layers are enough to obtain the same perplexity as the standard transformer with the same number of parameters. So they have the same number of parameters. It's just that they activate them sparsely when forward propagating, which is much faster and needs much less memory. And this results in the same perplexity when language modeling. So essentially means that the performance is on par. And also they say if they integrate with prior sparsity approaches, that's where they achieve the Terraformer. They can do fast inference on long sequence, even with limited memory. This results in performance competitive to the state-of-the-art on long text summarization, which is another thing where their model is state-of-the-art or equivalent to state-of-the-art while being much more sparse, much more memory efficient, and much faster. So yeah, we'll dive into this. The architecture, it's quite a mess. Like there are engineering tricks, and you know you have to wonder a little bit, what came first, like which trick came first and which trick necessitated which other trick. But we'll go through the architecture, through all the different pieces, and you'll see what this is all about and where the savings are done. All right, if you enjoy content like this, don't hesitate to subscribe. I don't want to do the other YouTubers show the graph. I'll do this. Here's the graph. So many of you are not subscribed. I mean, look at that. Excellent. All right. So the point with the sparsity gains is that if you implement them somewhere, then that part is fine. But then another part is still dense and is still the bottleneck. So you kind of have to introduce them everywhere. So if we look at a classic transformer model, and they specifically, I think, refer to like the stack of attention is all you need and so on. So what they have basically is they have two attention modules. So there's attention 1, I think there's attention 2, and then there is this feed forward layer. Okay, so we're going to take care of all of those right here. Attention 1 is called self-attention. So if I have a sequence coming in here, The self-attention would be essentially attention in between the elements of the sequence. The second attention block is, I think, encoder-decoder attention or something like this. The variants vary a little bit right here, but I would have sort of a second stack of this right here. I would have a input sequence right here. So this would be the input. This would be the target sequence that I'm about to decode. Maybe this has some causal attention. Who knows? The second layer of attention here is specifically attention that goes to the encoder sequence right here. So it's attention in between the encoder and the decoder, and the feedforward. So this essentially, these two mix all the information of the different tokens together, and the feedforward layer simply takes a single embedding of a single token and feeds it through a feedforward function. So all the tokens are handled by the same feedforward function. The first thing this paper does is it essentially eliminates the distinguishing between the self-attention and the attention between encoder and decoder, and I think that makes sense. That's also what a lot of other models do. So famously, BERT is an encoder-only model, GPT is a decoder-only model, and if I understand them correctly, they're simply taking the encodings from the source and then just prepending them to the target or something like this. Safe to say there are lots of things that one could do right here. But what I wanted to say is that we now need to replace each of those things with a sparse version. So we need a sparse feedforward, and we also need a sparse attention block. So how are we going to achieve this? First, we're going to the sparse feedforward layer. Remember, a feedforward layer is, I have a sequence of embeddings. So these are all vectors. And these are all embedding vectors. This is a sequence of embedding vectors that came out of the attention module, right? And the feedforward layer essentially is a matrix, and I simply pass each of these through a matrix. In fact, it's not one matrix. I think it is usually two matrices. One matrix that sort of, well, that's not how you draw a matrix. Like this, and then like this. Okay, so you kind of blow up the dimension in the middle, and then here there is a ReLU non-linearity in between. And the point is what I already said, you'd feed every single token by itself through this function. So this becomes like a large token. Then there's a ReLU, and then this would become sort of a token of the input dimension again. And you feed this token through as well individually, which give you this one, and so on. So in essence, we have a vector, right? A token, all the tokens are independent. We have a token, and somehow we need to make this sparse. Right now, it's a dense multiplication twice. So there's two matrices right here, and we have dense multiplication, right? So what do? The first thing they say is that, well, given that there's a ReLU nonlinearity right here, right? There's a ReLU. A lot of the things here essentially are going to end up being zero, right? So it makes sense. It makes sense to do sparsity here. Now, I don't follow that entirely. I guess half of the stuff will end up being zero, yet the sparsity goes much further. So, but maybe they justify why they can set some things to zero. Not entirely sure, but I found that reasoning a bit shaky. But here is essentially, you don't need a reason to introduce sparsity. If it works, it's good. So here's how it works. First, and this is what I found a bit confusing. So it essentially starts on the right, then it goes to the left. But I guess it's easier to start on the left. So what we want to do, you see here is that input vector, right? And here is that first matrix. So the first matrix is of dimension D model, which is the same as this dimension, and DFF, which is the feed forward dimension. And usually I just multiply that together, which would give me a vector in the dimension of the feed forward layer, right? Which I then send through my ReLU. However, what I want to do, I want to compartmentalize. I want only certain columns here to be activated. Right, so essentially say, I already accept that a lot of my things in my result are going to be 0 because, they will go to a ReLU anyway. So I'm going to accept that some of the things will already be 0. So let's say all of these, I already accept they're going to be 0. I don't even need to calculate the matrix multiplication between the vector here and let's say this column right here. I don't need to do it because after that, they will become 0 anyway, so who cares? So I'm simply going to decide that some of the things are just going to end up being 0, and they justify this by saying, well, there's a ReLU, so some of the things are going to be 0, but more. Here's like, 6 out of 8 are going to be 0. And now I only need to calculate the remaining columns, and that is the sparsity right here. Effectively, they subdivide the whole matrix into these compartments. So we'd have 2 different compartments right here. And in each compartment, only one column can be activated at the same time, right? I think, yeah, there's one of them, it's decided on one of them can be activated, and only that one needs to be loaded from memory. Only that one needs to be calculated as an inner product with the vector. And so the cells here where an actual value is going to be are sparse. Now the question is, how do we decide which ones we're going to activate? By the way, if you can see then for the second matrix, the same thing applies. In fact, I can use that same mask from here, and I can again say, well, in the first module, column number 3 was activated here, right? So row number 3 of this matrix needs to be activated. The other ones don't matter because they're 0 anyway. So there's a 0 coming in right here, being multiplied with this row. Who cares what the result is? The input is 0. Actually, well, people care. It's 0, right? But it means you don't even need to do it. You can simply just load the rows that are potentially non-zero. So yeah, how do you decide? How do you decide which ones you should load from memory? Essentially, you're simulating. You're already pre-committing to a ReLU pattern, right? So this is how you do it. Essentially, you take your input vector right here, and you're trying to somehow, we're going to see how that works, we somehow come up with a vector with a binary vector with numbers between like 0 and 1. So everything right here is like a 0.1, 0.5, 0.3, 0.8. So every single entry has a value. Every single entry will output like the probability that that particular element should be non-zero. And then you simply sample from that distribution and use a straight through Gumbel, a softmax, in order to backpropagate. So they also do a lot of tricks right here. I think they mentioned that in the forward propagation, they even sometimes need to do to pass just the softmax output instead of the actual sampling. So there's a lot of engineering tricks to actually get this to work. But safe to say, that's during training. We care about inference. During inference, you sample exactly 1 per module that is non-zero. Okay, so you have 2 different workflows. The workflow 1 goes here, decides what needs to be non-zero, right? And then given that information, you can do this feedforward layer in a sparse way. But that is all useless if this right here is not sparse. So this is actually not sparse, but it is low rank. So they say, well, in order to figure out which things need to be non-zero, we technically don't need as much information as, actually propagating information. So what we can do is we can have a low rank. Essentially, it's another feedforward layer, again, doing this blowing up the dimension to the feedforward dimension, but we make it low rank. So instead of blowing up the dimension in between, we shrink it down, right? You can see right here, we shrink it down to a low dimension, and then we go to the dimension of the feedforward layer to decide which things are 1 and 0. And that's a thing you're going to see often in this model, is that they make use of low rank combined with sparsity. And it's also a bit of a trouble that I have, because for some things a low rank approximation is fine, but there's a reason we have dense multiplications everywhere, because sometimes it's not, because with a low rank multiplication you essentially restrict your function space to a very, very small subspace. But it seems to work. So the trade-off here is that you get to do this sparse, which means that the time it takes decreases and the memory, but you have to, this here, over this is new, right? You didn't have to do this before. You could simply do the multiplication. So this is going to add to your compute, while this here is going to be faster. And now it's about whether or not you can make this side sufficiently low rank such that the gains over here are more than the time that you have to invest to compute this mask at the first place over here. Again, for these particular problems that they look at, it seems to be working, right? But these kinds of trade-offs, it's not guaranteed. Like, it's not so clear to me that it would, just work. Like, it's not straightforward that trade-off would be positive right here. There might very well be problems where this rank right here is just too small to carry meaningful information. You need to make it bigger, and that would sort of vanish all the savings you make over here. Because these savings are, essentially linear in the sparsity, and this right here is essentially linear in the low rank dimension. So there's the trade-off right there. So here is how you can express this. You can essentially express this as the original multiplication with the first matrix, ReLU through the ReLU, then times the controller output, and all of that then goes into the second multiplication. That's how you can represent it mathematically. That's not actually what you do, right? Because here you still have the full multiplications with the weight matrices, but it will result in the same thing as this formula. All right, so that is the sparse feedforward layer, and they do show that it decreases decoding time quite a bit, and interestingly, it also doesn't degrade performance too much. In fact, you can see right here, this blue line is the average of the baseline models. And if you don't go too sparse, you still have quite good performance. So this is quite close. Only if you go more sparse does your perplexity here start to suffer. I think that is one of the surprising things, that there is a level of sparsity you can go at where you're actually considerably faster, while your performance doesn't degrade yet. Again, can very well be because for the problems we look at, they're not difficult enough to really make use of the capacities of the dense models. Okay, so feedforward is done. Now we go to the attention layer, and the attention layer again is split up into two parts. In fact, they don't even really deal with the attention mechanism itself. What they actually care about is, in order to do attention is something like, I have my queries and my keys, and I do an outer product, and I normalize by something that I can't remember, and then I multiply by my values. This is the attention formula, And what they care about is how do I get the queries, the keys, and the values. In order to make attention itself sparse or long range or efficient, they rely on different techniques that from other papers. So for example, they will later include the performer and the reformer architectures, which make attention itself sparse or efficient or low dimensional. However, in this particular paper, they care about how do we even get these matrices. And usually you get Q by multiplying your input by a weight matrix like WQ. You get key by multiplying your input by a key weight matrix, and you get V by X. So all of these are dense multiplications. And obviously, they now become the bottleneck. Once we have the sparse feedforward layers, the dense layers in the attention layers become the bottleneck. The question is, can we use the same trick here as we did before? And the answer, they say, is no, because the structure of the feedforward layer here was such that it had the ReLU in between, right? So, and that's why they argue. So naturally, a lot of things are going to end up being zero, which we can exploit by just making, just a few more things zero, I guess. But they don't want to do this right here, because here, like, none of the things necessarily are going to be zero in the output of these calculations. So the Q or the K or the V, they don't have many zero entries. So it might not be justified to go sparse and just say, well, make stuff zero. So what do we do instead? Instead, we look at this diagram here. So on the top, you have what the current attention mechanism looks like. As I said, there is a dense layer essentially in front of each of these three matrices, which is that's exactly how you get the matrix in the first place, right? We're going to look at a thing which they call a multiplicative layer. So this is this mult right here. And the multiplicative layer potentially could replace the dense layer. However, they go a step further and they say they end up with this architecture right here, where they have a multiplicative layer, then so one multiplicative layer for all three matrices that is shared, and then one convolutional layer for each of the different matrices, which is going to make stuff even faster. And then they drop kind of this dense mechanism right here, and they simply add right here. Again, I'm pretty sure this works right now for these particular problems. Maybe because the problems don't make use of the parameters, or the original models were just poorly engineered. They never actually needed all of these parameters like this one, and we're all fine. This could also be the case. So we have two things to look at inside of the attention model: the multiplicative layer and the conv layers. And these kind of go together. And it also goes together with what's usually done in the attention mechanism, which is multi-head attention. So I'll draw a diagram of an attention mechanism for the about 500th time, but you have some sort of a sequence, right? And every sequence, I'll replicate the sequence over here. So every sequence emits what's called a query, which is a vector, some vector, which are the queries, and also every element in the sequence emits a key. So the keys are also some vectors, and the keys are also some vectors, and then routing is done via inner product overlap. So probably these would be routed together, these two would be routed together, this would probably be routed here, It can also be routed to multiple stuff, but you route essentially via inner product. So that's how you construct the weight matrix or the query key matrix for then multiplying by the values. The idea behind multi-headed attention, which is what's usually done, is that let's not only have one such block, let's actually have many such blocks in parallel, right? And instead of using the entire vectors that are output right here by, for example, that are in Q are the queries, right? Q is a matrix, and every row or column, don't exactly remember, is one of these vectors right here. They say, hey, let's, instead of, so Q is a matrix, let's say every row, let's just say every row. If I'm wrong, then, just reimagine. So instead of taking the entire vectors here, like the entire vectors as queries, we split the vectors into, in this case, into 3 parts. And this first part right here, that becomes the query for this attention mechanism. The second part becomes the query for that attention mechanism. And the third one becomes the query for yet another attention mechanism. That's multi-headed attention. Same with the keys, same with the values. And yeah, so now we're prepared. So what we want to do right here is we want to take a token, and remember, we now need to make a query. Let's say we want to produce the queries, right? So from this token, we need to produce a query vector, not only one, but number of heads many query vectors from this token using some sort of a linear layer, some sort of a linear function. So that's how we do it. They say we have this matrix right here, the weight matrix D. And what the weight matrix D is, that has the same dimension here as the input and has as many rows as we have different attention heads, right? So what we're going to do is we're going to element-wise multiply. And I would also add right here broadcast, right? Broadcast. So if you've used NumPy or TensorFlow or PyTorch, you know the broadcasting operation. So the broadcasting is done, this is of dimension 1 right here. The broadcasting is done between this 1 and this S right here. So this is going to be broadcast into this form right here. And you can see now, I mean, it's just an element-wise multiplication. So all that is like differently scaled versions of X in each dimension, right? So each row is essentially X a little bit shaky. So let's double shake X for the bottom row, okay? But this already is now a vector, one vector for each of the attention heads. Now, since element-wise multiply is probably not going to get us very far, we also multiply this by an actual matrix, but instead of multiplying it by a D model times D model matrix, again, we go into a low rank regime and simply say, okay, we have this number M, and that's going to be a reduction on our dimensionality. So this isn't D model by a D model matrix, which would probably be expensive. It's a D model by M matrix. And out comes this. So this is going to be the query vector for the first attention mechanism. Sorry, no. This is going to be the query vector for the first attention mechanism. And this is going to be the query vector for the second attention head. I meant to say head. Okay. There is a thing, like they don't just choose M arbitrarily. They in fact choose, I believe, S times M equals to D model, right? That is their formula. So if they split into S different heads, like in this case you see S is 2, then M is 3. And that has a very particular reason, namely, they say with this particular construction of the element-wise multiply followed by the multiplication by this weight matrix E, if we do it like this, then they have a theorem. Where is the theorem? There's the theorem. The theorem essentially says that they can represent an arbitrary permutation. So they say the minimum thing that we have to be able to do is to take X and kind of permute it. So to place every single element of X in the output wherever we want. So essentially, they say every part of X should be able to be forward propagated to all the attention heads or to any of the attention heads. And I have a theorem that says that if they construct it like this, any permutation is within the realm, is within possibilities for some matrices, for some weight matrices D and E. So that's kind of their justification of, well, we can represent all permutations, so it can't be too bad, right? Yeah, I found a little bit of another way of seeing this. If you look at this with the element-wise multiply and so on, it is easier to understand this as, let me try to draw this up maybe over, over here. So if you think about it a little bit, it is like, so you have, and you also look at the formula, this formula right here. You can clearly see that this is in fact a matrix multiplication again. So you have, I would say you have, if you look at this as D times X times E, where X here is a matrix that has zeros, but X on the diagonal, it's X, right? Which would give you, it would give you sort of a, so D is kind of this shape, then X is that shape, but only the diagonal is filled with X, and then E is like that shape. So, and D and E are fixed matrices. So you can see that what this multiplicative layer is doing essentially is it defines outputs. It defines outputs. So these are the number of outputs, and this is the dimensionality of the output. And what you're able to do is in some higher dimensional space, you're able to manipulate the coordinate system scaling a little bit arbitrarily, but you cannot mix the individual dimension freely. You can simply, in that high dimensional space, for a given mixing of dimensions, that's what these matrices here do, for a given mixing of dimensions, for given linear projections from the low dimensional to the high dimensional space, you're able to manipulate the coordinate system. So if you learn, you need to be able to find matrices D and E such that for arbitrary samples, the manipulation of the coordinate systems there makes sense. It's a little bit like, like doing a PCA or something on a data set, right? But it's just like during training right here. So yeah, I'm not sure. Again, this is quite a loss. This is quite a trade-off with an actual dense layer right here. But it's interesting to see that it works, right? And again, this is only conceptual right here. If you were to actually do this, you would lose all the benefits that you had. And again, you can see a little bit that the trick here isn't necessarily sparsity, but mostly low rank. This is mostly like a low rank function. Yeah. Okay, so we have the multiplicative layer. We end up with the queries and the keys and the values for each attention head. And now we're going to, they essentially say, okay, we could do this for every one of the three things, or we simply do it once, which would give us this property of the permutation being able, and then we can do something even cheaper if we want to get the individual matrices, right? And so the trade-off here is, well, here still every permutation was possible for the different matrices. So the Q could have different permutations than K, than V, or different functions. Here we're simply going to resort to one function, one mixing or shuffling around of the dimension, and then we're going to do something even cheaper, which is this convolutional module. And this convolutional module is also fairly simple to see. So this output y right here, I'll draw it again over here. You have two vectors right here, and they say it somewhere. They say the dimensionality somewhere. So you have two vectors, one per attention head. This is the output of the multiplicative layer. And presumably you would have those per token, right? We just looked at one token, but the next token, let me draw it in this color, the next token would also have them. And then the next token would also have two of those. All right, let's do this. So what you'd get is a tensor that has the sequence length, L. It has the number of heads, what's S, I guess, or number of modules. And it has M, which is that essentially that low rank dimensionality that the keys and queries and values live in. And they simply treat this as an image, and then they run a convolution across it. So the convolution is going to be, let me see if I can draw this properly. The convolution is going to be across these two. So the filter is going to be like this, and then in all the dimensions. So like this. Yeah, I'm terrible at drawing, but the filter essentially is going to be F in the dimension of S, F in the dimension of L, and M deep. And you have M filters of those. So you have an S by L by M tensor here, and you transform it also to an S by L by M tensor. Essentially, you can just think of this as a regular convolutional layer. And what does the convolution go over? Remember that the multiplicative layer simply works on a single token. It mixes, it kind of it is able to shuffle around the tokens' dimensionalities a little bit to permute them a little bit in the best case. And in all other cases, it essentially manipulates the scaling in a high dimensional space. And now with the convolutional layer, what we can do is we can bridge a little bit of information already between the tokens even before we go into the attention module. So given that the convolution is across the L and the S dimension, it means that for the S dimension, information is able to be passed between neighboring attention heads. And for the L dimension, it means information is being able to be passed between neighboring tokens in the sequence. So that potentially gives some sort of a positionality to tokens, because now that there's a notion of being close together. And also it gives maybe a little bit of a meaning to different attention heads, because the attention heads up until this point, they've just been kind of unordered independent things. And now they hang together a little bit. All of this is sort of one of the things why the exact conclusions of this paper are going to be hard to assess, even if they do ablations, right? They, at the same time where they introduce efficiency, they also introduce entirely new ways of sort of doing things. They introduce new paths where information can be passed from between things. And so it's very hard to point down exactly where things go right and wrong. So this was the sparse or rather low dimensional attention module. Again, this is first one of these multiplicative layers, which is element-wise multiply followed by matrix multiplication to a lower dimension. And then that is followed by these convolutional layers right here. So they call this whole thing a multconv. Right, if they combine all of this together, you can see right here, the blue with the shade is the average of the baselines. This is perplexity, so lower is presumably better. And you can see up to some noise, all of these things are fairly consistent, right? They follow the trajectory of the baselines quite neatly. Some are even kind of a bit lower, this one right here. Though I'm not sure if there is exactly confusion, because so the F right here is the filter size, right? And the S is the sparsity in the multiplicative layer, so essentially how many attention heads it splits stuff into. And you can see right here, there's a conv, there's just a conv, and there's just a mult, but the F is with the mult, which confuses me because the F is the filter size. So technically that should be with the conv, I guess. If the authors are watching, please leave a comment if I'm wrong right here. I'm confused. In any case, they show that the baseline transformer don't particularly do that much better in these NLP tasks, or even do worse sometimes, as you can see right here, though everything is pretty much within like a standard deviation than these scaling transformers. So this architecture that we've discussed right now is this scaling transformer. The last thing to do would be to add a sparse loss layer, so they can replace the dense layer with a multiplicative layer similar to previous sections. This speeds up decoding time, they say, but may degrade perplexity. Results are in the appendix. So the loss layer might be the last refuge of really dense things to do. But remember, due to the fact that in the feedforward layers we sample from this distribution to really be sparse, or in fact we might do argmax right during inference. That's where the speed up comes from. During training, we actually have to forward propagate the softmax from time to time so that the training works. And that means that the benefits of sparsity are lost, because if we don't hard sample ones and zeros, if we soft sample them, then all the rows are still activated and we need to track everything. And the same goes, I think, a little bit for batch inference. So if I have batch inference, even if I hard sample, right, different samples are going to have different activation patterns. And therefore, with enough samples, all the things are going to be won somewhere. And therefore, I probably need to load the entire matrix right here from memory. I need to do the multiplication with the entire matrix. Possibly not for all the vectors, but also possibly something like a GPU probably wouldn't care that some stuff is zero. It's going to be as fast just to do all the things at the same time. But that might be a hardware limitation. Okay, so that was the scaling transformer, and now we're going to supercharge the scaling transformer, which makes it into a terraformer. I don't think there's any relation to the tool Terraform, but we're running out of names of formers, so yeah, this was the last refuge, I guess. So what they do is they use essentially the architecture from the attention from reformer. So yes, we focus on the locality sensitive hashing attention from reformer. Was that reformer? I thought that was perform. I am confused by my own stuff. Reformer, yes. so they do two things, right? They have an architecture for long sequences. While integrating sparse attention layer into a scaling transformer, we notice the architecture is suboptimal. That's what I said at the beginning. Separating decoder self-attention and encoder decoder attention is not necessary anymore from the perspective of efficiency. We remove the encoder decoder attention. That I said that at the very beginning. But just concatenate the encoder representation before the decoder tokens. So they replace the encoder decoder attention by essentially two attention blocks. That is that. Okay. I guess there's no performer in here, just the reformer. So the LSH, I've done a video on this, locality sensitive hashing instead of full attention. So if you have really long sequences, as I said, you need to compute inner products between all pairs of nodes right here, of tokens. And this is cumbersome. There are various techniques to speed that up. One is LSH, locality sensitive hashing, where you essentially create hash buckets and then you hash all the vectors inside of it, or all the inner products become hashes, and you look for essentially hash collisions that indicate where you want to calculate and check, and everything that's not a hash collision you don't need to check. So locality sensitive hashing has been long-standing technique to make inner product search in high dimensions, or inner product computations, and looking for the most close inner product in among very many elements very fast. So they borrow that from there. And then also they include the recurrent blocks. So recurrent blocks is, no, that's later. First, it's the reversibility. All of this is just so similar. Reversibility is also apparently in reformer. And what reversibility means, it's kind of this architecture right here. So again, we have two attention and then one feed forward, right? The second attention replaces the encoder decoder attention. And reversible means that instead of having one strand, like one flow of forward propagating information, right? One flow of information, we have two. So there's I1 and I2, input 1 and input 2. We have two information flows forward, and then every function that's applied is applied to one flow and added to the other flow, right? This gives you this. And this one right here is simply forward propagated as a residual connection, essentially. And then x2 is taken. So the flow of the actual function would be this right here, right? You can see this is the flow of hitting all the functions. And you can also see that we always have a signal for each of the functions. We always have a signal that travels without being touched by the function right here. Okay, so that signal right here, and this is the signal right here. And that makes the blocks reversible. And that means that I don't have to keep activations in mind. This limits the capabilities a lot. So an example for non-reversible would be, well, this here is non-reversible because unless I do like a linear function that goes from exactly the same dimension to the same dimension that is non-degenerate, unless I do that, I cannot possibly reconstruct the input right here, like the signal right here, x, from the output y. Not even for a single one of those blocks, right? It's not possible for me essentially to do this. Or, so the reversibility changes that. Essentially means I can always reconstruct from these signals, I can reconstruct the intermediate activations, and therefore I don't need to store them, because in a normal neural network, as I forward propagate, I need to store a lot of intermediate stuff, like right here and right here, in order to then, during back propagation, I need those things because otherwise I couldn't calculate the gradient. So I need to store the activation somewhere. Reversible networks, reversible blocks do not have this property. They do not need to store because they're reversible, and they're made reversible not by changing the individual modules like this or this, but by simply having this construction of the two strands of information, and the modules simply apply between the two. It's a pretty smart architecture, but one has to say it has very often significant trade-offs, because these things being reversible also brings some properties, like there are a lot of functions you cannot express anymore because you need to keep everything reversible. So again, I think for the problems they particularly look at here, it might work. It might not work for all problems. I think that's a bit of a general thing in this paper right here. It's more like we're going to have to test for every new task we tackle, or new challenges, new modalities, whether these things still hold. The last thing they build in is recurrence, and they say it's for generalization. And that is, if I understand it correctly, it is they use simple recurrent units, not like an LSTM, because they say that would be too slow. So simple recurrent units, they're still fairly complicated. Like I've looked them up. I didn't know what they were. They're still okay complicated. So it's not just like a recurrent layer. It's actually, it has gates and so on, like a bit like GRUs or LSTM cells. And if I understand correctly, this goes between, so as I said before in the feedforward layer, that every single token goes independently through that. If I understand this correctly, this introduces a recurrent connection in between these. Did I understand it correctly? Okay. We also add recurrence to the feedforward block of Terraformer. Recurrent layers allow information to propagate in time, even in a single decoder block. Okay, I think I understood that correctly. So within the feedforward block right here, there is a recurrent connection between the different tokens. Every token goes independently through that, but now we introduce actually a sort of dependence or a function that goes from the first token to the second to the third and so on. A recurrent, small recurrent neural network. And again, one can only speculate why they have this in here. I mean, they say that the results on C4 are minimal, which is their language modeling task. And they say the biggest benefits are when they do like these toy tasks where you need to copy a decimal digit, and then you can train on 128 digits, but then you can test on 256, so it's over 2 times longer than seen in training. So they really make this point that it's for generalization, though it is very, very odd. Like, this is a very odd addition. I could get them until, like, here it says, yeah, okay, you go for long sequences, that's cool. Long sequences are cool. It's cool if your model can, also do long sequences, fine. Then memory efficiency, okay, so given that this is all sparse and low rank and so on, you also might want to use less memory, cool. But then recurrence for this is quite an odd choice, I feel. And it could be that it simply didn't work. Like, so they also say that the Terraformer here in sort of these tasks like summarization, that it sort of beats or matches state of the art, matches much larger models and so on. I can imagine that their numbers were slightly smaller, like slightly worse than kind of the baselines, and they were just looking for something to add to pump up those numbers, and this worked. If this is the case, if, that's a big if, again, it's very dangerous because it might work for these particular problems and not for others. If not, if this was really just like an idea they had and said, well, it'd be cool if that's in there, then, you know, good. Like, I'm willing to accept that as well. All right, so that was the Terraformer, and here you see, so the Terraformer now has over a 37x speed up on, it's a considerably large model, but for this large model, it requires less than 100 millisecond per token of decoding time, while not degrading in performance too much. So that is, I think, quite an achievement, even if it's only for particular types of tasks like these here. It is quite an achievement, and it's a bit of a shame that the speed ups are only for, like, they're only so huge for the really huge models. I guess it makes sense because these effects are often compounding, you know. So it, for you and me with like our regular old computers, laptops, it maybe won't make that much a difference in terms of speed. It might make a difference in terms of memory because of the reversibility. But other than that, yeah. But it's good for, like, if you want to work with larger models, but you don't necessarily have to compute and you do inference, this might be something for you. They specifically say that not everything has been tried yet. They still don't do quantization, which could yet deliver another speed up. And there's also lots of things to do to actually speed up training. Maybe there's a way to get around this Gumbel softmax need to forward propagate the true softmax from time to time, and so on. So lots of engineering, lots of kind of choices that are interleaved. Very hard to say where gain comes from, but undeniable, gain has been made in huge form, and that's cool. All right, tell me what you think. I'll see you next time. Bye-bye.